Alright, so our essential question is how can we factor polynomials of the form x squared plus bx plus c? Now, it's important to note that this first group of factoring problems that we're going to deal with are the easiest type because the coefficient in front of x squared will be 1. When it's of that type, it's a pretty simple methodology to solve these problems. Once you figure out how to do it once, you should be able to do it relatively quickly every single time. So just like multiplying binomials and trinomials, you want to be able to do this pretty quickly and in your head the more that we do them. So even though I'm going to show you how to do this via the X method, you want to get good at them or well enough at them to where you are able to do something in a simple form like this in your head. So what is factoring? How do we factor? Well, we talked about factoring being sort of a reverse distribution, taking out a GCF, remember? We're still going to be doing that. So it says writing a polynomial as a product of factors is called factoring. Remember, a factor is each of these binomial terms. So x plus p is a factor, and x plus q is a factor. So when we change a polynomial to its factored form, we are factoring. It says to factor x squared plus bx plus c as the product of x plus b and the other quantity x plus q, you need to find p and q such that p plus q equals b and p times q equals c. That's pretty confusing wording, but all that is saying is you're going to be looking at two things. You're going to be looking at your c and you're going to be looking at your b. This and this. These are the most important components of factoring here. And this is the question that you're going to be asking yourself, and I'm going to write it down and I encourage you to do the same. You're going to ask yourself, what multiplies to be C and adds to be B? So let me write that down. What multiplies B, and I put that in quotes, and adds, and it'll make more sense when you see an example, I promise. B, C. That's the question you're going to be asking yourself the entire time that we're factoring. Now, what is the X method, what is the box method, etc.? Those are just different ways we can organize these factoring problems to make them visually sometimes make more sense or stand out. So this X method is just a way to help organize these problems. It is different than the way the book teaches you, but it's not wrong. So here's what I like to do. I like to sort of separate everything out so as not to cause confusion. I think of that C, remember. Oops, I switched this around. This should say what multiplies to be C and adds to be B. Change this. There we go. I'm going to label this product, and I'm going to label this sum. And I'm going to label this product, and I'm going to label this sum. What multiplies to be the last term, what group of numbers multiply to be the last term, and also add to be the middle term. You're looking for combinations of numbers that meet those qualifications. The P and Q part are those two numbers. The P and the Q are the two numbers that add to be C or that multiply to be C and add to be B. That multiply to be C and add to be B. Okay, once we do one of these, it will become clear. let's try 1. Go ahead and write that down. We're going to attack this using the x method. And the more that we do these, you will find, hopefully, that you will no longer rely on that x method to come up with those numbers. So, write the first one down and then draw your little x. So the question that we ask ourselves is, what two numbers multiply to be 5 and add to be 6? So here's what I'm going to do with that x. I'm going to think, okay, what multiplies to be 5 and adds to be 6? What two numbers would that be? 5 and 1. Yeah, right? 5 plus 1 is 6. 5 times 1 is 5. Does that make sense? So 5 and 1. Are those two numbers, that p and that q, yeah? So, what does that mean? That means that these two numbers make up those factors. So x plus 5 and x plus 1, and we factored it. Does that make sense? So that's all you'll be doing the entire time for these simple cases. And again, the more that we do these, you shouldn't have to set up the x. Or even some of you won't ever have to set it up at all. You can think, what just multiplies to be 16 and adds to be 10 in your head? Sometimes you will have to use a factor tree, and it just depends. You're looking for different combinations. So let's try the next one. I'm going to put that product up top. What multiplies to be 16 and adds to be 10? 8 and 2. 8 and 2. These two form my factors. So I know that this is x plus 8 times x plus 2. Yeah? Again, not every case is going to be as simple as that. Sometimes it's like, well, I can't really think of something. Let me set up a factor tree because maybe there's a set of numbers that I'm not thinking of. Now, when it comes to a quadratic, which we talked about having that square term, you are going to be thinking about two numbers. So when you make a factor tree, let's say you're looking at 16, 8 and 2, and then that's 4 and 2, and that's 2 and 2. You can't think about all of these numbers simultaneously. You'll have to think about either 4 and 4, right? Or 2 times 2 times 2, which is 8 and 2, right? So you have, or 16 and 1. So you have to think of combinations like that. Does that make sense? Yeah, so that's how a factor tree can be helpful when you're coming up with those two that make up your factors here. Any questions? All right. This is, again, just what happens when our number is negative. Well, what multiplies to be 12 and adds to be negative 8 this time? Negative 6 and negative 2, right. Because negative 6 plus negative 2 is negative 8. Negative 6 times negative 2 is positive 12. So we have negative 6 and negative 2. So my factors are x minus 6 and x minus 2. And you could always double check if you didn't think that you did it correctly by multiplying these binomials. You should get x squared minus 8x plus 12. And we will get that here. You have x squared minus 2x minus 6x plus 12. And I find that this is x squared minus 8x plus 12. So that does work. Does that make sense? Yes.
Why is it minus negative 6 or plus 6?
Well, because if you do plus 6, you won't get this out in the end. FOIL it or do the distributive property right, you will not get this. So look, think about it. X plus 6, you said x plus 6, and x minus 2. Well, first of all, do 6 and 2. When you add them, 6 and negative 2, do they add together to be negative 8? No. And that will produce something that's not negative 8 as that central term. Does that make sense? Yes.
Were negative 6 and negative 8 related?
Negative 6 and negative 8. They are related in the sense that the negative 6 plus the negative 2 will get you the negative 8, and the negative 6 times the negative 2 will get you a 12. Yeah? So, again, that's why I make this x, and it can be helpful for some people. Others of you, you'll say, like, well, I don't really need it, and that's fine. But others of you, it will help the visual. The negative 6 and the negative 2, these two central terms here of this x have to be related to this negative 8, and since they have to add to be, they have to sum to be, right, negative 8, and they have to multiply or be the product of 12. Yeah? Okay. Questions on factoring so far? You think you got it? Okay. You can try the next one on your own if you want to. I'm going to go ahead and show it on the board here. Alright, so same thing. I'm going to put the product on the top. What multiplies to be 21, negative 21, and adds to be positive 4. Yeah, negative 7 and, what was it, negative 7? 7 and, yeah, 7 and negative 3, right. 7 and negative 3, perfect. So those two central terms make up my factors. X plus 7, x minus 3. Does it matter what order I put these two in? No. Because remember, commutative property says that A times B and B times A are the same. Okay. Excellent. Speeding through these notes. Your book does not discuss this right away, and I don't know why. It should. So I made this up on my own. One of the things that you will have the temptation to do, and I've had the temptation to do, and I mentioned this before, is start utilizing the factoring method that we're going to look at tomorrow without pulling out your GCF first. Remember how I said the very first thing you want to do is look for a GCF if you have one? Because that will simplify your life. We will look at some more complicated techniques tomorrow where we handle coefficients that are not 1. But sometimes those methods can be extremely difficult. Yeah? So, something to help us, if we find a GCF, is we need to pull it out. Okay? So, what do all of these terms have in common that I can pull out? What is a GCF? A 2. Right. If I pull out a 2, now what am I looking at in the parentheses? X squared plus 2x minus what? Yeah. And really, all I have to do here is the exact same factoring method. Does that make sense? So that's why it's important to pull out that GCF first, so you don't all of a sudden get lost in the complicated factoring technique, when really all you have to do is pull out that GCF and then factor it in the same way that we've been factoring things. Yeah? And we've already factored this before in the previous problem, and what do we say those two factors were? X plus 7 and x minus 3. Yeah? So now that's completely factored. So that's why it's important to look for your GCF first, again, to avoid having to put yourself through a headache for something like this. Now, will that always be the case where you can pull out a GCF? No. But more often than not, sometimes a problem that seems impossible, because not everything is factorable, and we'll discuss that. While many things are, not everything is. And sometimes something that seems impossible is only impossible because you didn't pull out a GCF. Yeah? So you don't want to get the wrong answer and be like, oh, this is not factorable, this is impossible. And then it is possible because you forgot to log it. Yeah.
How is the 7 negative 3 out of 2?
2?
Yeah.
Oh, you're right. What did we say last time?
We said that last time, but there's a folder last time.
Oh, you're right. I meant to make that an 8. You're right. I meant to make that an 8. Yeah. Yeah, so now that becomes a 4. And then that becomes a 7. And I'm just, you're right. Thank you. Again. Okay. Beyond that mistake, does it make sense? And thank you for pointing that out. Okay. Here's another case that you may see. You will often encounter, instead of a 1 in the front, you'll have a negative 1, or some sort of negative coefficient. And it is almost always the case that it is easier if you pull out that negative coefficient first. Meaning that you don't want to deal with a polynomial that has a negative leading coefficient. Yeah? So in this case, I have a negative 1 as my leading coefficient. So what I want to do is pull out that negative. Okay? I'm pulling out that negative 1. I'm saying that that negative 1 is my GCF. And so I have to get negative x squared plus 2x plus 15 when I distribute that negative 1. So that means that in the inside I have to have an x squared, which makes sense because negative 1 times x squared will give me that negative x squared, right? And then I'm going to have a minus 2x, so the sign changes. And again, that also makes sense because negative 1 times negative 2x is going to give me that positive 2x. See what I'm doing? And then I have to take out a minus 15. Again, negative 1 times negative 15 is going to give me that positive 15. And now I can factor it in the way that I know how into the x method. So I'm going to ask myself again, what multiplies to b? Negative 15 and adds to b. Yeah, negative 5 and 15. Well, you're saying what multiplies to be negative 15 and adds to be negative 2. So it has to be, the bigger number has to be negative. So negative 5 and 3. Those are two things. These last two I cannot emphasize enough. When you get into more difficult factoring, and especially in Algebra 2 and Pre-Calc, everybody forgets this little trick. Okay? You don't want to forget that. Any questions? We have practice and then a word problem and then we'll be done. Alright, if you're watching this video, make sure to pause this and give alternate V's a try. Now, let me show you the answers. We are going to work 9 and 10 together, since I made those up. Okay, these are the answers for 1 through 8. And I'm going to go ahead and start working 9 and 10 for you. And then if you have questions on 1 through 8, let me know. get all of this? You have questions on any of this? So, pretty comfortable with this? Remember to look for GCF if you can. Look how much simpler this became just because we pulled out that 3x. And when we start looking at cubics, we will still apply these methods to make it easier. Because if you look at something like this and I ask you, well, where does this cubic function cross the x-axis? You're going to be like, well, wait, what? And you'll be wondering, okay, well, maybe I should just graph it, look at table. And really all you have to do is factor, and then set those equal to 0, and then use your product property, or zero product property, right? Okay, cool. One more problem. Word problem. And we're done. Let me read this problem to you. It says, a farmer plants a rectangular pumpkin patch in the northeast corner of a square plot of land. The area of the pumpkin patch is 600 square meters. What is the area of the square plot of land? This is something that, had I encountered your age, I would have just stared at for like 5 minutes, maybe. But you have to think of it this way. What in that problem is familiar to you? Area, right? An area of a square in particular. So what I think about is, okay, well, what do I know about this problem? I know a couple things. I know that to get the area of the square that I'm looking for, it's S times S, right? The entire side times the entire side. So I know in the end that what I'm looking for is really S squared. Yeah? Yes. Well, let's see if you get the right answer. Okay? So, the other thing that I have to look at is what I'm given in the problem. Even though this is sort of my money equation, I really can't do much with that. But I do know that the pumpkin patch itself is 600 square meters. So the area of this, that's 600 square meters. Yeah? Well, now I have to think about what that means in terms of what I'm given in the problem. How do I find this piece and this piece? How do I find this remaining piece? What will I have to do? Yes. Not quite. Well, we're going to get there. Yes. Nope. Yeah, it's a rectangle here. Okay. So, but I know the entire side is x, right? So can't I just say that this x that I'm looking for is s minus 40? Yeah? Then if I take this entire side, I subtract the 40, won't I be left over with this? Yeah? And can't I say the same thing? That the entire other side of that square minus 30 is going to be that missing piece, right? And can I also say that if I multiply those two, s minus 40 and s minus 30, won't I get 600? Yeah? Does that make sense? Well, this is a really tough problem because it's having you multiply this first because you still don't know what s is. You can't just say s minus 40 equals 600 and s minus 30 equals 600 unless it's what? A 0. Is this a 0? No. So we're going to have to use FOIL or whatever and multiply it out, right? Distributive property. S times s is s squared. S times negative 30 is minus 30s. Same thing with the minus 40. You get minus 40s. And then you have plus 120 equals 600. Yeah? You're right. 1200. Are you with me so far? So now what do we have to do? We have to combine our like terms, subtract 600 from the other side, and then factor it. So,
Subtract 12.
1200.
well, you want this to be 0.
Oh.
Yeah?
Okay.
So, go ahead and combine these. 30 and 40, which will be 70. So this is s squared minus 70s plus 1200 equals 600. Then you want to subtract 600 from both sides. You get s squared minus 70s plus 600 equals 0. Now you can factor by the x method, solve for the value of s, and then square it, and you'll finally get your answer. So go ahead and try to factor that, and then we'll check. Okay. So what were your two numbers that you put up there? Yeah. So we're looking at x minus 60.
Yeah.
X minus 60 and s minus 10. Now that would leave me with two different s's. Which one doesn't make sense and why?
Nope.
Why does 10 not make sense for an s? Yeah, it's too small. You already have from here to here being 40, and if this entire side is s, would it make sense that it's 10? So this is an extraneous solution. Remember that? So s equals 60 is our answer. Not the final one though. You have to square it, and when you square it, you get 3,600 meters squared. That, my friends, is your final answer. What is your way?
Easy way. So, you know that that's like a small portion and you want those into missing. So what you can do is find something that equals, find two numbers that equal 600. And so you can come up with 30 and 20 and then you will have the other one 600. And so then, if you add 30 and 20, or no, 30 and 20 and 40 and 30 and 30 and 40 and 20 that equals 6 times 15 is 16.
Huh?
I meant, she said 60.
Wait a minute. All right. Here you go.